All right, let's get started. Problem set number 8 is due tomorrow, as you know, by 2 p.m. Problem set number 9 is assigned on B-Space something like Thursday morning. We'll try to get it out Wednesday night, but I'm guessing Thursday. And my office hours today will be from 4 to 5. Talc tonight. Those are the only major announcements I had. Colloquium will be on Thursday, as usual, at 4 p.m., and that's on the formation scenarios for the solar system. Not directly relevant to the things we've been doing here in 7B, but obviously if you'd like to attend, feel free. Any questions on logistics?
Happy
First contact day? Last time we talked about galaxy distributions, and we said that there was some generic form for the space density of galaxies at a given luminosity. And because we're talking about luminosity, we could also translate that into in absolute magnitude, capital M. There was some confusion about whether I was saying mass or magnitude. I was talking about magnitude. And that has some functional form where there's a power law. So it goes as L to some factor of alpha. Alpha is typically around -1. And this describes the faint end of the luminosity distribution. Remember, sort of looks something like this. This is this power law. This is some sort of exponential cutoff. And there's some characteristic value here of L star, which is sometimes called the knee of the luminosity function. This is the Schechter luminosity function, e to the minus L divided by L star. We also talked about the Egan-Linden-Bell sandage theory as a formation scenario for the Milky Way and in general for very large spirals. And we contrasted that with the hierarchical structure formation theory. And the idea here is, while collapse is an important component of all galaxy formation scenarios, the difference here between essentially a single large cloud collapsing to the Milky Way and multiple small building blocks of clouds individually collapsing and then over time assembling themselves is quite a fundamentally different one, both theoretically and then also conceptually. And this is the idea that we have now as the dominant picture for how galaxies like our own are formed over cosmic time. So in this process of galaxy assembly, we talked about the need to have a cloud collapse in the early stages of the universe. And we said that there was an important time scale called the freefall time scale, which goes like Newton's constant g times rho to the -1/2 power. So it doesn't really matter the size of the cloud that we're talking about or the mass. What it only depends upon is the density. You've seen this before in a couple of different contexts. And the typical numbers that you get in the early universe for the early universe densities is something like 200 million years. So quite a large time to collapse on this time scale of star formation, but a fairly quick time scale for collapse on the time scale of the evolving universe. But a given cloud can't just spontaneously go under freefall collapse. Instead, it will have to cool sufficiently such that the cooling time scale is more rapid than the freefall time scale. We have to get rid of heat. And we showed that the cooling time scale went something like mu mh sigma squared. This is this velocity dispersion that we saw before in the context of ellipticals, divided by the number density times this numerical number, capital lambda. And it had units of watts meter cubed, so that everything sort of worked out dimensionally. There was a temperature associated with the gas, as we've seen before in the context of star formation, of mu mh sigma squared divided by 3k. And it should be also clear from our discussions of how you actually get cooling in a given cloud that cooling is going to depend upon the temperature of that cloud, in particular the relative velocities of various particles, and the number density of the particles involved squared. And so that's an important thing to keep in mind. And last, we concluded that the maximum mass of a collapsing cloud in the early universe would be something like 7 times 10 to the 12 solar masses. This in and of itself doesn't tell us whether ELS or HFS is correct, because this is enough mass effectively to make up the total mass of the Milky Way, except this is a very rare event to get a maximum mass of this size. Instead, what you wind up seeing when people start thinking about the distribution of gas clouds as they collapse is some sort of n as a function of mass, if you'd like, mass. And this just has some power law such that you get most of your small clouds dominate those clouds that collapse, and then you have your big clouds up on the high end. And a way to think about it is m mass, max, is up on this high end over here. We don't understand exactly what sort of drives this distribution of clouds that collapse on these different mass scales, but it seems sort of generically true that if you're going to wind up getting this overall structure of the universe where you have slight density and homogeneities, that you might expect little clouds to sort of reach some sort of critical density such that they could wind up collapsing. But the sort of whatever this power law is not really well understood at a very basic theoretical level. So that's kind of interesting. However, forgetting about the cosmology theory that would describe that you get more small clouds than you get big clouds, it's pretty clear that when we look, say, with the Hubble Space Telescope at very distant images of sort of protoclusters or even just random places in the sky, you do see a lot more of those little building blocks than you see in the local universe. And so those building blocks presumably are disappearing because they're merging with each other, or they're being accreted onto even larger galaxies nearby, and they're building up the whole mass and the structure of those galaxies. So we can see these assembly blocks kind of in situ. Are there any questions about that? Just a review of last time. Okay, so in thinking about galaxies, the idea is that you have individual gas clouds which themselves have gas, and they form dust, and they form stars. They wind up assembling themselves through some of the processes that we saw before, essentially just falling into each other's potential. There's some overall angular momentum associated with this system as depicted right here. And what you see is that the gas will wind up settling down onto the disk, and the stars that were formed at early times in those initial sort of primordial clouds, those stars might be on very large, wildly plunging orbits, which might make up the halo or the bulge. And then new stars will form in this disk here. So this is the picture of how we get population 1, population 2 stars within the Milky Way. I wanted to also just point out that as this gas settles in, if we start thinking about spiral structure, we sort of skipped over a good part of this going into the mathematics of it, but I thought it'd be important just to point out that to keep a spiral structure like this going, you'd have to have differential rotation as a function, that is, different velocities as a function of radius to keep this whole structure going. But instead, because we wind up having a circular velocity, so that the velocities are the same basically at all these different distances. That's an observed thing. That's how we infer dark matter. Over very rapid time, you wind up winding up all of these arms. This is why I said early on that the way that we think about spiral arms is not as structures that are all moving together, but instead as density enhancements of stars and gas that stars are basically traveling through. The pattern, as we see, the motion of these spiral arms is much slower than the motion of individual stars moving through them. Yes, Pauline?
So where in that theory would you get the separation of the population 1 stars in the halo and the population 2 stars in the disk?
So the idea here is that old stars, which would be population 2 effectively, in principle you could have population 3, but old stars form as these gas clouds are collapsing in the very early history of the universe, in the first billion years of the universe. Now, not all clouds have cooled enough after a billion years to collapse. So some of them may take another 5 billion years, right? So collapse is actually happening. We can see these things. You can see sort of primordial clouds sort of on the verge of collapse. But those are where the Pop 2 stars are formed. And because the stars don't really feel the viscous effects of what the gas feels when it shocks against other gas. Those stars, as they fall in, just basically continue on their orbits as if they were unimpeded, and they're not actually getting sort of dragged around by the gas that much. So that's population 2, and then population 1 stars form in spiral arms, effectively, in the gas that settles down into a disk. So that's how you get your 2 different populations and 2 different timescales. And of course, it's not a discontinuous thing where you only have really old stars and only really young stars. There is a sort of continuum of stellar ages. Yes?
Where does the supermassive black hole come in? Like, when in this process?
We don't know. That's a good question. When people think about the formation of supermassive black holes, there's a bit of a chicken and egg problem. We don't know whether the supermassive black holes were formed first in these proto clumps of galaxies and just maybe had a size of 10 to the 4 solar masses or 10 to the 5 solar masses. And then, then it makes sense that all of these little black holes will wind up settling down into the center. There's some sort of a sense of mass segregation. The heavier things will eventually settle down if they do feel enough of a drag. And that's how they would wind up assembling. So it's possible that supermassive black holes are assembled from supermassive, for less supermassive black holes that have merged into each other. That's one idea. The other idea is that perhaps you just had one of these seed black holes and all you needed is one within this. And then you had enough gas accretion and actually stellar accretion into the black hole over the history of the universe to build up the mass that way. But what it seems likely is that supermassive black holes were formed from the mergers of less massive black holes. And every time you get a merger of 2 large galaxies, eventually their black holes will wind up meeting and actually merging, actually producing a lot of gravitational waves while they're at it. How you get those seed black holes in there is another question. It may be that the initial stars, the truly POMP3 stars, the pristine stars that are formed without any pollution from previous stellar generations, those may all die in the form of black holes, and those black holes may be 10 solar masses, maybe even 100 solar masses. So it may be that you just start off with that. Or it may be that those black holes were formed way, way early in the Big Bang, and what's left over after sort of the Big Bang makes all of its particles that it's going to make. It's going to make basically the elements, that you also have a lot of little black holes around, and those black holes accrete. We have no idea where the sort of seeds are of supermassive black holes, but there's certainly lots of ideas. Okay, so let's talk about, just for a minute, the star formation within spiral arms. You can see sort of, this is a depiction, this is not an actual galaxy, of the dust lanes. You can see that the older stars are more diffusely positioned around spiral arms, and the newer stars are the ones right at the leading edge of these spiral arms. And star formation is largest, the star formation rate is largest in these spiral arms. The way to think about it is that you have this overdensity of gas and stars, and you have stars and gas moving through that overdensity and sort of loitering there and spending more time there than they ought to. And that's why you appear to have these large density contrasts. The way to think about this is as a traffic accident. Perhaps there's an accident down over here, and people are rubbernecking, and they're not actually stopping, but they're loitering and slowing up. So if you're looking down at this pattern right here, and you were just looking down at the pattern of traffic, you would say that there's an overdensity of stars right here. And you could say, especially if this accident, I don't know, this is taking it too far, this accident is actually rolling this way, you could see how the sort of overdensity might travel at a different speed than the overall stars coming through it. Okay, so what should be clear is that you have the stars and gas coming through this density enhancement. You get a compression of stars. If you think about this in a Jeans mass sense, or even a Jeans length sense to be more specific, when you compress gas that's pretty close to being critical, if you compress it enough, it might be able to go over the Jeans mass or the Jeans length. It'll be smaller than Jeans length. And then it could form stars. So this is some sort of self-propagating star formation. You have lots of stars being formed in spiral arms. those stars, many of them will actually form and be quite large and then wind up dying in the form of supernovae. They will expel lots of material. That expulsion of material is going to wind up moving very quickly. It's going to cause shocks. It's thought that in the shocks and the outflow of supernovae at later times, you can produce more stars. So this whole thing is just sort of cranking up the heat and producing more stars. So think about this now in the context of a gas blob moving through a spiral arm. As it moves through, it undergoes a lot of star formation as it gets compressed, and then it stops, or it ceases its very rigorous star formation. Or vigorous, not rigorous. It's not deriving anything. All right. So let's talk just a bit now about this galaxy assembly, not so much in the context of producing stars. By the way, I should say that these spiral arms are sort of propagating in the sense that every time you sort of take another step in time, you have more gas coming into the system, and as you do, gas leaving. So it is some sort of steady state of star formation. That's interesting in and of itself. What's not clear at all is how the spiral arms got to be there in the first place. Once you set them up, it seems like the dynamics are such that you can actually keep them going. But we don't really understand exactly how these spiral arms are set up and just continue to persist for very, very long times. It's an interesting question for galaxy dynamics. What is clear, though, is that rotation is quite important, and the origin of that rotation in the context of large galaxies, to be more specific, the origin of the angular momentum in the context of these large galaxies is going to come from the infall of these dwarf galaxies into an ever-increasing galaxy. Yeah, go ahead.
How is it that like in the thin and thick disks there can be like different stellar populations, and then I've also read that like you can have one disk rotating in the opposite direction as the other.
Yeah, I mean, that's a very unusual phenomenon where you could, again, it depends in detail on the accretion history of a large galaxy. If you had a galaxy like the Milky Way and it wound up swallowing another galaxy that was maybe a third the mass of the Milky Way, and it was coming in at the opposite direction as the motion of the spiral arms and all the stars, in principle, for a while, all of the stars in that other galaxy could wind up counter-rotating around, right? If it was as massive as the Milky Way, they would just destroy each other's potentials and kind of all bets would be off. So depending exactly on the ratio of the masses of the mergers, exactly on the orbits of the things that are falling in, and even what their stellar populations are and what the potentials are of the things falling in, that's going to wind up giving you some instantaneous new picture of this galaxy which just got bigger. And over time, how that all settles down is, a very complicated process. But in general, the way to think about it is the dust and the gas is going to want to settle down onto some pancake, right? And that disk is going to be and the sort of plane of that disk is going to wind up being dictated by the final angular momentum of the whole system. But the stars more or less sort of keep on going, and all they're seeing is sort of the Newtonian potential of the galaxy itself. So if they're on highly elliptical orbits as they come in, those stars could sort of remain on very highly elliptical orbits and just keep on sloshing back and forth. So thick and thin disk, basically due to different populations of satellites that have fallen in and produce essentially, an epic of a lot of gas falling, in which case you might get the thicker disk, and then the thinner disk might be formed as you get sort of smaller satellites falling in. In detail, that's not right. I mean, but that's sort of the broad brush picture of it. Okay, so let's talk about galaxy interactions. And in particular, what we're interested in knowing is how, when we talk about galaxies merging into other galaxies, are we talking about stars smashing into stars? Your intuition should say no. Let's come up with some numbers on that. And if not, what are we talking about when we talk about galaxy formation as these two blobs smash into each other? We'll do the first question first and the second question second. If we're talking about galaxies, here's a galaxy with lots of stars falling into another galaxy with lots of stars. if we want to now calculate the rate of collisions of stars, what do you think the relevant quantities are that we have to pay attention to? The density of stars. Cross-section of what? Okay, well, let's do that one first. What's the cross-section of a star? The radius? Yeah. Let's do radius of the sun squared, right? Yes. Yeah.
Can we just use their radius, or should we use something like, if they get really close, they're still going to interact?
Yeah, there's a gravitational focusing effect that might increase this by a few factors, but it's not huge. We're just going to come up with an order of magnitude number. Good. So this is 3 times, what's the radius of the sun?
7 times 10 to the 8th.
Times 10 to the what?
11.
11th what?
Centimeters.
No.
Meters.
No. 10 to the, yes, that's correct, 10 to the 8th meters. I have to do everything in centimeters and then convert 10 to the 8th meters. Good. Okay, so there's our number there. Right, number density of stars, what would be a good number to choose based on what we learned when we were thinking about dark matter? 1? In what units? Are you the kind of person that says like G and C and K equal to 1, and then you derive something and say that, M equals 1? You'd be a good physicist. What? In the local universe, it was 0.05 per cubic parsec. That's kind of a good number to remember. Okay, what else do we need to know? Yeah. Why do we need to know velocity?
Because if they're going faster, then they're going to collide faster.
Well, there'll be more interactions, right? So if we're going to come up with sort of a rate of one star in galaxy A hitting stars in galaxy B, A, B, that's just going to be n sigma v. So that's going to give us per unit time, and then we're going to wind up canceling the length dimensions. Well, I put in these numbers already, just to save some time. And we need to understand what we think the velocities might be. When talking about stellar dynamics and you're talking about galaxy fragments, how fast are they kind of falling into each other? What's that? Yeah, that seems right. How about 200 kilometers a second? That's a big guess, right? Again, that'll depend upon sort of the initial conditions that define where these two fragments are that are eventually going to wind up falling into each other. But given that we think the Milky Way is built up by fragments that wind up moving at velocity, and stars are moving at velocities of 200 kilometers a second around us, that's not an unreasonable number, actually. But it could be as low as tens of kilometers a second. It could be as high as 1,000. Yeah. Oh, that was just a wag of the pencil. Right, so the number here is 1.7 times 10 to the minus 20 collisions per year for star A, galaxy A, minus 20. That's for one star passing through galaxy B. So what's the total number of collisions of all the stars in A onto all the stars in galaxy B? Okay. So n stars in A, right? And then a time scale of them to pass through each other. And then this quantity here, rate. Okay, so what would be some good numbers here when we're talking about galaxy fragments? And remember back to these little dwarf galaxies that are found around the Milky Way. Remember what their total masses were in stars? 10 to the 10 is like a Milky Way. I want to think about masses of dwarf galaxies. Yeah, 10 to the 8 or 10 to the 7, that's fine. So we have a mass of one of these dwarf galaxies of something like, you want to say 10 to the 8 stars? That's fine. That's actually a pretty big fragment, say 7. And then what's T pass? Timescale for passage through. That's to go inverse to the velocity, right? If the velocity is really high, they're just going to pass through each other really quickly. Times what? Yeah, times some sort of size of the galaxy. How could we come up with a number that's not ad hoc for the size of that galaxy? Yeah, we could do that, but based on what we posited, in particular for the number of stars and the number density of stars. Times the number density is just going to be n stars, right? R cubed, thank you. Okay, so that cancels. Our galaxy, something like n stars divided by n, little n, to the 1/3 power. There's a 4 in there. So 10 to the 7. So let's do this in parsecs. So we figure out the size of this galaxy in parsecs, so we don't have to do a conversion. 10 to the 7 divided by 10 to the 5. 10 to the 7 divided by 0.05 times 4 to the 1/3 power. This will be in units of parsecs. What number do we get? No, 1 to the 1/3 power. So this is about 0.2, right, down here. So we can make this effectively 10 to the 8, thereabouts. And 10 to the 8, so 8 divided by 3. What's that? Almost 3. So let's call it 1 kiloparsec. And that's actually right. So the typical fragments you get, 10 to the 7 stars, typical size of 1 kiloparsec. And remember, these are fragments that have already collapsed, right? And now they're going to merge into another galaxy. So you can put in these here, 10 to the 7 stars. The time scale for passage is going to be of order 1 kiloparsec, or maybe it's 2 kiloparsecs, divided by this velocity. This is, remember, we had this in kilometers a second. Typical numbers from this, what did I have down? Something of order 5 times 10 to the 6 years. Just 1 million years for these stars to strongly, for these galaxies to strongly interact. And this rate of 1.7 times 10 to the minus 20 collisions a year. So what do we get? Five times 1.7 is 10. So that would be 10 to the 8. 6, that's 10 to the 14. So 10 to the minus 6. So you need 1 million galaxy collisions before you even had one star hit another star. This is small. It's not at all obvious that it had to be that's the case, but for the most part, when we think about galaxy collisions, apart from the gas, which are indeed going to shock against the other gas, if you just think about the stars, those stars are just going to pass right through each other. They don't even care. All they're doing is just changing the gravitational potential that the other galaxy will wind up seeing. Yes?
There aren't like any like black holes or like really compact objects that might
I mean, sure, in detail, right? Right. What Leo was saying is that you're going to also have gravitational focusing. It's not just the cross section is seen by one star viewed by another. It's going to see some gravitational focusing that, as it's over here, it's going to wind up being pulled in, right? So its effective cross section is going to be larger. So at the factors of few level, that will indeed change. But having a black hole, I mean, a black hole of mass, 10 to the 4 solar masses, assuming it's not so much, doesn't have a mass comparable to that of the total numbers of stars, which would be really unusual, is a pretty small perturbation in the overall potential, right? Right. So when galaxies collide, what actually happens with them is that they only interact, the stars only interact gravitationally. And they're not actually smashing into each other. So this is kind of interesting. Now let's think about a case to understand how they indeed are interacting gravitationally. Let's think about a case where we have some star from galaxy A moving through part of galaxy B, and we'll have 2 stars from galaxy B. As this star and galaxy, remember, they're not going to actually hit each other, so they're just going to sail right through. As this star from A passes through B, what's going to happen to these stars here, which might otherwise be at rest? They're going to wind up coming together. And in fact, if we sort of think of this as a movie, they're going to wind up kind of moving slightly behind where this star is passing through. This is, frame 1, frame 2. And then at late times, those stars are going to be closer together and moving with some velocity. Now, if these stars are at rest in sort of frame 1, when this is very far away, and when this star is passing through the middle of them, these stars now have some kinetic energy associated with them, right? So where did that kinetic energy go or come from? Yeah, so star A is going to slow up. So star A is slowing up. Now what happens when star A is passing out? It sees a very different potential than it saw when it was going through. It sees a much more concentrated distribution of stars than it did when it was entering the system. So you wind up getting this extra conglomeration of stars, this focusing that winds up causing this thing to try to pull backwards. So there's an extra force here. So the kinetic energy from A goes to B. There's a focusing of the gravitational potential and a shrinking of the size of B. This causes effectively a drag force. So as you pass through, even though A is not hitting any of the stars in B, as you pass through, A feels this extra force back and says, oh, I really want to be back over there, right? This is how you wind up changing the potential. And that extra force, the drag force, goes like 2 factors of the velocity squared. Sorry, it goes like 2 times, no, it goes v times v, velocity squared. And why is that? Well, one is you can imagine that if the velocity is very high, as this thing sails through, there's really no time to transfer the kinetic energy from A to B. And the other is if you go very, very fast, then you wind up not focusing very well. right? And so you don't see anything at all. So in fact, if this thing was sailing through very, very fast, the drag force would actually be pretty small. So F drag, as it turns out, goes something like g squared m squared density of the system divided by v squared of the relative velocities. M now is the total mass of B, and rho is the density of B. Again, the drag force is going to go down as we increase the velocity because there isn't that time to transfer the angular momentum, and the concentration of the stars behind it, leaving it in its wake, is going to be less.
Yeah.
So it should be -2?
Oh, yeah, thanks. Yeah.
Also, when we say massive B, it seems to me like if you were traveling through a galaxy, it could be sort of vaguely defined what the total mass is that you're considering.
Yeah, but if there's lots of stars as this thing is passing through, it's going to be much easier to transfer that angular momentum and much easier to do that focus. For the same mass but a much lower density, right? It's not going to transfer that that kinetic energy as easily. It's not going to do that focusing as easily.
So, I mean, when you say massive B, you're taking the mass of the entire galaxy?
Yeah, because it's seeing the whole galaxy. Yeah.
Why doesn't mass of A show? Wouldn't you think that the force?
Oh, sorry. This is the drag force felt by one star as it passes through. But of course, all those stars are going to feel a similar force. Yes.
About like relative velocities of the two.
Yeah. So you zoom into the frame of one, and you see these other stars passing through it. Yeah.
We're in the frame of theta mass.
Yes, that's right. Yeah. And there's the sort of constant of proportionality up here of where C is of order 10 to 100. It depends on the distribution of the stars. Yeah.
So B is like a group of stars around that one star, or?
Think of B now, if you want to, as an entire galaxy fragment, and think of A as an entire galaxy fragment passing through B. Now this is frame 1, and frame 2 is that B actually gets sort of flattened out, and A also gets flattened out, and it's feeling this force backwards, force drag, but it continues out at some sort of lower velocity than it had when it was coming in. So if this is V1 and this is V2, then V2 is going to be less than V1 because of this drag force. But you get this flattening effect. Yes?
If Galaxy A and Galaxy B collide, could Galaxy B end up stealing some stars from Galaxy A?
I mean, it depends on the velocity, right? So I think if the velocity dispersion of B is comparable to the infall velocity of A, then there's no real difference between all the particles moving this way and sort of moving in a swarm. Then they'll have a comparable potential, and then you can imagine just stealing effectively. You're right. What happens, of course, is that there is some sloshing effect, right? Because you're feeling these drag forces after enough of these encounters, because eventually this is going to get out to a large distance and then fall back in. This is what we saw in the movies. And those stars will sort of slosh back and forth until they're not feeling an appreciable drag force, or another thing comes in and they wind up getting their potentials perturbed yet again. Yeah.
So, I mean, we would use the same formula that we were talking about, like one star from A, or considering like in our system just one star from A, or the entire galaxy A.
Yeah, and what we're going to do now is think about not sort of two galaxies of comparable mass, A and B, but think now about a large galaxy and think about some smaller galaxy falling into that. Or maybe not even a galaxy, maybe just take a gravitationally bound system of stars like a globular cluster and see what happens to that, because it will feel this drag force over time. But it's a very, very long time scale, as we'll see. All right, so let's take some globular cluster, which is at a very large distance. It doesn't have to be a globular cluster, but we can assume it's a small galaxy fragment. So this could be a globular cluster, or it could be a small galaxy fragment, what have you. And it's going to be at a large distance from a very massive, say, spiral galaxy. And we're going to now see how this moves through. Now, if there was no drag effect, then this would just move on circular orbits. But if there's a drag effect, what's going to wind up happening? Over time, it's going to wind up spiraling in. Now, this is a very, very special case where I'm having the globular cluster or the galaxy fragment move along the plane of where the spiral arms are. But you can imagine generalizing this to having something falling right through, right? To do this in detail, you need a supercomputer to watch how every particle, or in this case, every star, winds up interacting gravitationally with every other star. So if you have a million stars, you've got, a million squared calculations you have to do at every time step. Okay, so the drag that this system is going to wind up feeling is just going to be c g m squared divided by 4 pi r squared, because the density, as we know from our dark matter studies, goes like v squared divided by 4 pi g r squared. So that's just plugging that back in there. So all of a sudden we see some interesting things. The drag force now is going to be much less at larger radii. That's sort of intuitive. And some of the tricky things that I've done here is that I've assumed velocity is the circular velocity. And I've assumed at large distance it just keeps on continuing out to 220 kilometers a second or whatever the number is, right? That it's a flat rotation curve. Again, we're just trying to get a toy model here to see what the typical timescales are for something at some distance falling into the Milky Way, which was otherwise on a circular orbit. This drag will act as a torque on the system. And does anyone remember what that is? So we can put in R for that over there. And we know this has got to be the change of the angular momentum with respect to time. L now is angular momentum. What is L? M. Yeah, in this case, if it's circular orbit, what's cross mean? Yeah. We'll assume the mass. Now, this is the mass of the globular cluster or galaxy fragment. We'll assume again that velocity is approximately constant. This is our little trick. And R is going to be changing with time. So this is just going to be m v dr dt. This, if we put in for what we have over there, we have c g m squared divided by 4 pi r. And now we can solve for some sort of sense of a cluster lifetime, the time it takes for it to continue to orbit without falling in very rapidly into some sort of spiral pattern. This dimensionally is just mvr divided by some sort of time scale. And we can solve for all this stuff, and we wind up getting a time scale for the cluster. Again, you would do this. If you were doing this in detail, you would actually do the integrals properly here, right? Because as you change r, the left-hand side is also going to wind up changing. But just dimensionally, this is about right. You wind up getting 2 pi v r initial squared divided by c g m, big M. Now, c, as I said, is some number between 1 and 100. It depends on exactly the details. This number is 156 gigayears divided by v at 220 kilometers a second. Ri, and so our initial 10 kiloparsecs squared m divided by, say, 10 to the 6. Oh, sorry, this is the galaxy fragment, or the globular cluster mass, to the minus 1. Is that a long time?
Yes.
That's a long time. What's the age of the universe?
14.
Yeah, so this is an order of magnitude longer than the age of the universe. If, then, and here's the conclusion from this. If you had a galaxy cluster, or a globular cluster, which was at 10 kiloparsecs from something that had a circular velocity of 220 kilometers a second, it would orbit around, it would feel a drag force for sure. It would be sort of having its orbit slowly decay over time, but it would wind up, there should be a minus 2 here. Oh, no, that's right. It would wind up having its, more or less stay, it would basically stay intact gravitationally for the whole history of the universe. If I start decreasing this number, so I figure out a way to get a galaxy fragment, say, within 1 kiloparsec of the Milky Way, it would be very rapidly destroyed, because then it would be 1 divided by 10 kiloparsecs. So this would be a factor of 100 smaller. So on a time scale of, say, 2 gigayears, you would wind up completely destroying that system. Make it even smaller, that is, get a galaxy fragment falling into the Milky Way on some sort of highly elliptical orbit, have it essentially pass through the center of the Milky Way, and it's completely destroyed on a very, very quick time scale. What should be clear is that when we look at these large galaxies passing through each other and essentially perturbing each other's potential, is that for a while they're going to pass through and they're going to more or less elongate each other. So this drag force kind of manifests itself as a tide. Let's show some pictures of tides. Oh, that's too... This is a low surface brightness tidal tail, which is why I had to turn the lights completely off, and taken with a Hubble Space Telescope. And what's probably happened here is you had a large spiral. You had another fragment which went right through it, and it wound up not getting completely disrupted, but getting stretched out. And you see this long tail. And so this tail is going to wind up getting even more stretched and then fall back in. And all of the stars associated with this tail are going to wind up eventually making its way into building up this galaxy into a larger size. What do you notice about this tail? It's big. What else do you notice? It's blue. It's brighter farther out, really? Yeah. You could squint and it looks kind of like that. That's true. I think the dominant thing here is that it's blue and it's got pockets of star formation. Why might it be that if we have galaxies collide, why might that be some sort of episode of large amounts of star formation? Exactly. So you're getting this compression of not just the stars, but also the gas in that galaxy, if there's indeed any gas left. You get a huge burst of star formation, and you can use up almost all the gas in that original galaxy. And then you're left with just a bunch of stars, and they all wind up falling back in.
So, we would also expect, like, the gas to heat up.
Yep.
And wouldn't that be, I mean, I guess the effect is negative in case of, like, spiral galaxies, but that would be, like, that would inhibit stuff.
That's true. If it had enough time to sort of heat up without cooling down, then you would inhibit star formation, right? Because the gene's mass would change enough. But what's actually happening is as it passed through on a very quick time scale, while the heat sort of gets a bump up, you compress the gas pretty dramatically, and then it wants to collapse. Good. When we look out around the Milky Way, and remember this is a way of visualizing the sky in galactic coordinates. So the galactic center, the black hole at the center of our galaxy, is basically right here. The galactic anticenter is here along the disk, and the north galactic pole is up 90 degrees. Anyway, what we see are these large streams, not unlike the galaxy that I just showed you before. And this is the Large Magellanic Cloud and the Small Magellanic Cloud. What do you think this stuff is? It could have passed through us, or if we think we understand the orbits well enough, it looks like it's just orbiting around us in a somewhat elliptical orbit, and it's getting this tidal stretching from just even being part of the potential of the Milky Way. And it may be that if you follow this around, there's actually a big sort of plane of all this star stuff that was left over as this tidal tail was formed. So here's the sort of picture. And this is a pretty good example now. This is obviously a depiction, not any simulation here, just to show you, for illustrative purposes, what it might be as you sort of leave behind this long trail of star formation. These are very, very small galaxies. That's a very large galaxy. And what's fairly interesting and dramatic is when you have galaxies of a similar mass colliding, and then you wind up getting these very large tidal tails. Here's a zoom in on a small part of the head of that galaxy collision. This is the antenna galaxy. And what do you notice here? Really reasonably blue here. Why is all this stuff red? Dust. There's a lot of dust. In fact, there's a tremendous amount of star formation. I forget how many supernovae there have been in the last decade or so, but I think we've seen something of order 5 or 8 supernovae just from this galaxy, because there's a tremendous burst of star formation in this violent collapse. Okay, so any questions on sort of tidal streams, tidal tails, galaxy interactions, drag force? All right, so let's move on to the bigger picture. Oh, I should have just put this down. And talk about clusters of galaxies. So now we're sort of abstracting even farther away from galaxy formation and galaxy interactions and thinking about conglomerations of galaxies. Now I've turned the light off again because it's such a cool picture. Do you see that? Yeah, okay. So this is the Virgo cluster, basically the largest nearby cluster to us. 15 million light years away, about 1,000 galaxies associated with it, and it's 15 degrees on the sky, right? So this is 30 full moons of size on the sky. It's a tremendously large system. And then the next really big one, which is about 100 megaparsecs away from us, has something like 10,000 galaxies. And because it's just its distance, not necessarily its size is sort of comparable, it's only 30 arc minutes on a side, right? So this is half a degree. This is basically the size of the full moon. But there's 10,000 galaxies gravitationally associated with each other in the form of these clusters. And in the coma, if you zoom in, this is a Hubble Space Telescope image. Basically, all of these little things here are galaxies associated with the coma cluster, and there's this thing called the central dominant galaxy, which is a giant elliptical galaxy. And you can imagine at the center of these potentials where you've had lots of galaxy interactions, that stars are really happy sort of congregating there over time. And what you wind up seeing in very rich galaxy clusters is this sort of single large elliptical, which has presumably benefited from a tremendous number of passages of individual galaxies that have gone through the center of this potential, and it's ripped out those stars, and they wind up settling in to that galaxy. What's interesting, of course, is that we can add up the total light from those galaxies obviously trying to understand which galaxies are gravitationally associated with each other by understanding the distances of all those galaxies. And we can come to some conclusions about the presence or lack thereof of dark matter on these large scales. So we can add up the total light in a cluster. So for instance, we said in an individual galaxy, what was the mass to light ratio? Say for a spiral? Yeah, like 4 for an elliptical. So this is a spiral. An elliptical might be 30 to 50. In a cluster, we want to know what this mass to light ratio is. For the coma cluster, the typical velocity dispersion is something like 1,000 kilometers a second. Okay, let's think about what I mean when I talk about velocity dispersion now. Well, somebody tell me. What's 1,000 kilometers a second in a cluster of galaxies? What's the meaning of that? Yeah, it's the typical relative velocities to each other. So if I was going to look at the coma cluster and I was going to get a spectrum of 10,000, coma cluster, I was going to, 10,000 galaxies, I'd have some overall velocity associated with the whole system. In this case, it'd be moving away from us because there's a redshift effect. And there'd be a total number of stars as a function of velocity. And this might be moving away from us, I forget the number, at a few hundred kilometers a second. This velocity dispersion right here, is that right? Yeah, that's about right. So, no, so 100, sorry, megaparsecs times 71. No, sorry, this is about 7,000 kilometers a second. This velocity dispersion here is order 1,000 kilometers a second. So I just take spectra of all of these galaxies, and I'll see something that looks like either a Maxwellian distribution or Gaussian or something. And it's the typical width of this. Right? Just like we think about in the context of stars and elliptical, the exact same thing is observable. And the exact same physics that keeps the elliptical galaxies sort of going in a happy equilibrium is also at play for a galaxy cluster that is in itself happy equilibrium. Instead of happy equilibrium, we might call this some sort of virial equilibrium. And that gives us in overall mass. For a spherical system, it's 5 times the radius times the velocity dispersion divided by g. We know the distance to the coma cluster, so we can figure out what the angular size translates into, and that's about 3 megaparsecs. And that gives us a typical mass of 3 times 10 to the 15 solar masses. So this is something we can observe. That's something we can observe. That's something we infer. 3 megaparsecs. What was the size scale of the local group of galaxies of the Milky Way? Does anyone remember that number? Larger. Yeah, about 1 megaparsec. So this is only a volume that's 100 times larger than the volume of the local group of galaxies. We said we had about 40 of them in the local group of galaxies. And in this galaxy cluster of Coma, we have, 10,000 galaxies in a volume that's only a factor of 10 larger. So this is a much more dense, much more rich environment. So there are actually quite a large number of interactions in this environment over time. Anyway, so here's the mass, and I'll just tell you what the luminosity is. L is 5 times 10 to the 12 solar luminosities. And so the mass to light ratio of coma is something like 300, depending on exactly how you do it, to 600 solar masses divided by solar luminosities. Order of magnitude larger than in ellipticals, which itself is an order of magnitude larger than in spirals. Yes?
Is for mass to light ratio, do we use stellar mass or trivial mass?
You tell me.
I thought it was stellar.
No, that's the important point of the mass to light ratio. So if we just, what's the mass to light ratio of the sun? It's 1, right? Because the sun doesn't have any appreciable amount of dark matter in it. And so its mass is dominated by the star stuff that we say makes up and contributes to the overall luminosity. The mass, which is really nice, is something that we can just get from the motion of individual galaxies relative to each other. You just infer that by assuming that they're in some sort of virial equilibrium, right? If they're not in virial equilibrium, then that galaxy is in the process of either exploding, or the galaxy cluster is in the process of exploding or collapsing on itself. And since we see lots of galaxy clusters throughout cosmic time, all in this sort of happy state where it looks like it's more or less a spherical ball of galaxies, we can infer that most of these things are going to be in some sort of virial equilibrium. So there's going to be a mass associated with it. And by the way, there'll also be a temperature associated with it too, right? And I gave that at the beginning of class. So there's a temperature associated with that galaxy cluster. And there's likewise a mass, which doesn't care what the origin of that mass is, right? So, in fact, dark matter was not found originally in the context of rotation curves, which is how I presented it to you. I didn't lie to you. I just presented first to you the evidence of dark matter in the context of rotation curves. But the original inference of dark matter came from this Caltech professor named Fritz Zwicky, who took spectra of galaxies in nearby clusters, and he wound up seeing that they had velocity dispersions of 1,000 kilometers a second. He knew about the virial mass. He knew about a virial temperature. And he plugged that in. He said, uh-oh, there's not enough galaxies to make this up. There is missing mass. So the original concept of missing mass came from Zwicky. I believe it was even in the 30s. And it was essentially forgotten for decades. I mean, he didn't forget it, but other people did. You can sort of guess what this guy's character is like based on this picture. And there's a famous story about him. He didn't get along with any of his colleagues, as you might guess, at Caltech, and he called them all spherical bastards because they were bastards no matter which direction you looked at them. So if you're trying to be really mean to your peers late at night, you can call them a spherical bastard, I guess. Anyway, Zwicky is a very famous character in the history of modern astronomy, involved in the early days of observations of supernovae and understanding what they were, involved in neutron star observations of black holes, well ahead of his time. Okay, so we look at the coma cluster, for instance, and we say, well, there's too much mass for how much galaxy light there is. How do we know that not all that galaxy light accounts for the baryons? That is to say, how do we know it's dark matter? How do we know it's not ordinary stuff that isn't somehow associated with stars? Well, you can imagine sort of taking deep H1 maps to figure out how much neutral hydrogen there is, and people have done that. Turns out there's not a whole lot, or not enough. What's another way that baryons could hide themselves, not in the context of stars which are bright, but in the context of something else that we might see? Dust? Yeah, they could be in the form of dust. Not enough. Keep going. Dim stars, it could be, and in fact this is a hot topic these days because some people have taken spectra of some elliptical galaxies and shown that there are some very faint stars that account for maybe even a factor of 3 more stars than there were before, just because we didn't get the initial mass function correct of the stars, but it doesn't make up that much luminosity. It doesn't make up that much mass. So we weren't so off on the mass to light ratio there. Well, right, so I want to avoid having to talk about dark matter. I want to figure out a way to say in 1933 that you're the spherical bastard, Fritz, and it's all baryons. Could be black holes, yeah. Let's assume that those galaxies are like our galaxies, not a whole lot of black holes. I sort of hinted at this already. M virial, there's also a temperature, a virial temperature associated with this sigma. Temperature large. Gas ionized. Ionized gas in a spherical potential that's deep, interacting with itself. Oh, man. This is really like pulling teeth. So how do we know it's not in baryons, the missing mass? And that's because there's a virial temperature associated with the cluster. And this temperature is high. It's in fact much larger than the ionization potential of hydrogen. And so for typical numbers of clusters, we wind up having 10 to the 6 to 10 to the 7 Kelvin. 1 million degrees, actually 10 million degrees in the cases of the most rich clusters. So given that, how would we now infer how much mass there is in the form of ionized hydrogen atoms?
Take its spectrum, that region.
And?
And there should be like a spike around the lambda that's associated with that temperature.
That's true, but what's the physical process that would give rise to an emitted spectrum of hot gas? It's a thermal, it's semi-thermal. Bremsstrahlung, yeah. So we get Bremsstrahlung like crazy. Bremsstrahlung. If we look at the spectrum of Bremsstrahlung, I've shown this to you before. Just like the Schechter luminosity function, there's some sort of knee in this. And I nu goes like number density squared of the electrons, temperature to the minus 1/2 power, e to the minus h nu divided by kt. Actually, it's very similar to the Schechter formalism, right? Completely different physics. Here we've got temperature to the minus 1, so now alpha would be minus 1, e to the minus h lambda. H nu. So as I increase the temperature, I'm going to wind up having I'm going to change this thing here. The point is that I can measure some typical h nu, which is going to be associated with the virial temperature. Actually, it's kT. Okay, so now I can measure this so I can infer the temperature. How do I know how many particles I actually have? Because if this gas turned out to be electrically neutral, which makes sense, number density of electrons is going to be comparable to the number density of protons, which was a way of us making a number density of effectively the total number of baryons that were associated with this gas. The luminosity in this Bremsstrahlung, by the way, what wave bands would this be observed at primarily? What? Ultraviolet or even shorter wavelengths, higher frequencies, X-rays. So in 1935, I couldn't tell Zwicky, no, you're the spherical bastard, because X-ray astronomy hadn't been invented yet. That was like Back to the Future 5 that they decided not to make because that would be pretty boring for most people. Like, go back and tell Zwicky he was wrong. So luminosity divided by volume is 1.4. This is for Bremsstrahlung radiation. 1.4 times 10 to the minus 28 times the quantity Ne squared T to the 1/2 power in units of watts meter cubed. Number densities that we wind up finding out is something like 300 per meter cubed. So the mass in the hot gas, hot ionized gas, is just 4 pi divided by 3 r of the cluster cubed times Ne mh. Right? This is the mass density of all the particles, because we're ignoring the sort of contribution from electrons, just looking at the protons, and you get something like 10 to the 14 solar masses. So the conclusion here, and which I'll write over this part of the board, when comparing the mass in the hot gas, it's pretty much larger than the mass associated with stars, but that is smaller than the mass associated with the cluster as a whole, and likewise dark matter. Unless these galaxies are vastly different, they have like a lot of black holes in them or something. The only other place you could hide gas that's not associated with stars would be in the form of hot gas, which we can see Bremsstrahlung radiation from. This is called the intra-cluster gas, or the hot intergalactic medium. Hot IgM, not ISM. That's interstellar medium within a given galaxy. So here's an X-ray image of a cluster. Let me put this down a little bit more. You can see the size scale here of 2 degrees. And you get this diffuse X-ray emission, although you do get some emission associated with some galaxies. Why would that be the case? All right, what kind of galaxy do you think M49 is? Oh, it could be an active galaxy. That's true, right? Because it could just be some jet that's pointing at us and we get some AGN activity. Assuming it's not an active galaxy. How would you get a lot of hot gas around a galaxy? Would it be a little tiny LMC-like galaxy, or would it be a big galaxy? Big. It would be kind of a giant elliptical galaxy. So you can get, around large ellipticals, you can get hot X-ray gas, which is associated with the gravitational potential of that elliptical, and that's how you get this. But this whole gas, while sort of centered on the central dominant galaxy, this giant elliptical, it's actually more diffusely positioned and more associated with the gravitational potential of the cluster as a whole. You see this in lots of different systems. This is an image from a paper that I wrote a few years ago where we looked at a gamma ray burst which occurred in a very large, or near a very large elliptical galaxy. And what's interesting is that there was an offset from where the center of the cluster appeared to be by optical images, and where the X-ray center of that cluster appeared to be. And there it looks like there's another X-ray bright source up there. It looks like this is some sort of cluster merging into another cluster, which is pretty interesting. So we see this all the time. All right, so any questions about that? Okay, so let's talk about how we're making masses, measurements of masses that don't have to appeal to a virial concept, and that's the way in which we tried to figure out what the masses were of potential macho objects and using gravitational lensing. But the cool thing about gravitational lensing in the context of galaxies and galaxy clusters is that instead of this being a micro separation of images, that is micro arc seconds, is what you get when a star micro lenses or gravitationally lenses another star in our own galaxy or in the LMC, is that when you have a galaxy whose mass is very large, that's fairly near the line of sight of a distant galaxy, what you can get are different pathways to image that galaxy. And you can see this is not a great image, but here's a little dot here, a dot here, a dot here, and a dot there. That's this image of the same galaxy. So you actually have now lensing which spreads out the images of these galaxies. And this is a better example of it, where you have 4 images of the same galaxy because of lensing. And some more dramatic examples are here of individual elliptical galaxies now lensing almost perfectly. These are called Einstein rings, lensing almost perfectly background galaxies. Why are the background galaxies almost always blue? Because they're old? Because their stars are younger. Yeah, that's true. Uh-huh. They're farther away because they're behind them, right? So they could be at, the light of this galaxy could have left sort of 5 gigayears after the Big Bang. The light from this galaxy could have left 2 gigayears after the Big Bang. So yeah, you could think about this in a galaxy assembly process, that you have this elliptical galaxy. But why would an elliptical galaxy, or just some sort of gravitational lensing object, doesn't care what object is behind it? Why is it that preferentially we find an overabundance of blue galaxies? Yeah, it's that if you look in a volume of space back in the early history of the universe, most galaxies were blue and little. This is this whole building block concept. So you're seeing this just depicted right here, that we just more or less only lens blue little star-forming galaxies. Every now and then you get a lens of sort of a spiral galaxy, but that's incredibly rare. And I'm not aware of any lenses of giant elliptical galaxies by, say, a giant elliptical galaxy. It has to be a pretty chance alignment, right? You need to have basically a galaxy almost directly behind another galaxy. And what's interesting is that you get these ring shapes here, but even without having this galaxy directly in front of the other galaxy, if we had another galaxy up here, it would wind up having its shape sort of change just a little bit. This is what's called weak lensing. What you're seeing here is something called strong lensing. And we can imagine what weak lensing might look like by putting a dark, unseen system moving through the board here, moving through the screen on the left-hand side, and you see the effects that it has on the background galaxies. Can you figure out where it is? Do it again. Notice that you get this strong lensing effect when this source moves through, right? So this is something where I don't care that it has stars or not. It's just got lots of dark matter. It's moving through here, and it's strongly lensing this galaxy here. Notice how you get a counter image on the other side, and you get a perfect Einstein ring. Look at what's happening, though, on the outskirts, very far from that. You get this shearing effect, almost like a tidal stretching of the visual image of that system. We'll see it one more time. Just look at some of these little galaxies that are down here, and look at their shapes as this thing passes through. You can see the shapes are actually morphing. And indeed, that's what we get with large clusters of galaxies. This is an incredibly rich cluster of galaxies. Again, a Hubble Space Telescope image. And what you see are these giant arcs of galaxies that have been gravitationally lensed. And you see another giant arc up there. But basically all the blue stuff are background galaxies, and all the red stuff are foreground galaxies associated with this cluster. The entire potential of this cluster is lensing the light behind it. And you can see not necessarily giant arcs in all cases, but just sort of elongations that appear to have this sort of center of focus around the center of this galaxy. And this is very interesting because it means that if you can analyze the shapes of all these little things here, you can come up with a map of the gravitational potential that the light went through to give it those distorted shapes. This is what's called weak lensing. And weak lensing maps is the way that we can make very interesting images of where the mass is. Here's a very deep optical image actually taken from the ground, taken in good seeing conditions where the atmosphere was very, very stable. And you can see there's some problems here, like some of these stars are bleeding here up and down direction. But it's incredibly deep, incredibly uniform. And what the people that made this map did is they looked at the shapes of all these different galaxies, and from that they deduced where the mass was. And there's a huge mass sheet right here, just coming through this part of this image. Do you see optically that there's an overdensity of galaxies there? No. Do you see that there's a large overdensity of galaxies right around here? Maybe. Maybe there's a little cluster of galaxies, and this could be associated with this. What's very interesting is that irrespective of our ability to sort of count stars and figure out from virial constraints, what the masses are, we can just look at an image of large numbers of galaxies, both in the foreground and background, and we can make a measurement of sort of the integrated line of sight potential through this weak lensing map. So it's a way of us actually making measurements of cosmic structure without having to do galaxy counting. And what's so cool about this, and I'll end with this picture here, is that we can make measurements of where the gas is, and it helps us understand something pretty profound about dark matter. Look on the left-hand side, and what you see is that you have a bunch of galaxies which are associated with a cluster, and it looks like there's another smaller cluster right there. Overlaid are the contours of the weak lensing map, that is the gravitational lensing map, made of the background galaxies. So this tells us that there's two concentrations of mass. And what you see is that this is an X-ray image, and you notice that the gas is not associated with where the mass is. So what probably happened is that you had two clusters that merged into each other. So now this is getting to even larger scales than we started off with when we talked about galaxy-galaxy mergers. Two clusters which merged into each other. And the dark matter just kept on going through. That's what gave us these these contributions here. But the gas wound up shocking and staying behind where the two things actually met. And that's what gave rise to this X-ray gas here. So it tells us that dark matter is not associated with this X-ray stuff, right? There's really no way to wiggle out of the fact that dark matter appears to be something real. It appears to be some object which is quite happy passing through itself and stars and gas. And weak lensing does this for us. And so this is considered one of the best examples. This is called the bullet cluster of the evidence that dark matter is not just some sort of change of Newton's potential at large distances, but is actually stuff. Okay, so I'll end with that, and we'll pick up on Thursday with large-scale structure. Remember, office hours from 4 to 5 today for me.